This is a follow-up video uh, following an earlier video I made where we introduced forces. So I highly recommend you watch that video first, but the purpose of this video is to give a lot more details regarding Newton's laws. Newton's laws describe objects and forces, and the first law, as it says here, is objects at rest. An object at rest stays at rest. An object in motion stays in motion with the same speed and in the same direction unless acted on by an unbalanced force. Another way of saying that is objects keep doing what they're doing in a straight line, and in a straight line unless an unbalanced force acts on them. So some examples of this might be if you are sitting in your car going at a constant, going say at 50 miles an hour, and you have your phone on the dash for some strange reason in the middle of the dash, and you go around a curve to the right. Well, it appears like your phone wants to go to the left as you go around the curve to the right. Actually, your phone is trying to stay in the same place, and you are, in fact, you're leaving it, and it's trying to stay in the same place at a straight line. So there's a lot of different implications to this, and I'll give you a ton more examples and some demonstrations in class. But basically, things go in a straight line at a constant speed. Now, since they want to do that, they want to resist that change in motion, we can actually quantify how badly they want to do that. And so what we call that here is inertia. Inertia is the resistance of an object. The resistance an object has to change its state of motion. Inertia, that's what the word inertia means. So a couple examples of this might be, if you have a little ball like this is a racquetball. We can hit it pretty easily with a pencil or a pen, and it moves. This is a very similar sized ball, but it's solid steel, and we can hit it, and it sort of behaves differently. It has, you could say, well, this steel ball has more inertia than this round racquetball. Well, we actually have a word for that. We can measure it, and we have a word for it, and that word is called mass. So maybe you've never heard this before, but really what mass is at its very heart is it's the measurement of an object's resistance to change in state of motion. Masses also can be found by counting up the number of protons and neutrons in an object. And that's because that's actually what has mass. And so if we count all those up, we could predict, and you could say definitively that this one has way more protons and neutrons than this one. But at its heart, mass is really its resistance to change in motion. The unit, of course, we use for mass has already been covered. It's the kilogram. And now if we move on to the second law of motion, I think this one has a lot of ramifications. And it says that unbalanced forces always cause acceleration in the direction of the net force. And remember that a net force is the same thing as an unbalanced force. The proportions are acceleration is directly proportionate to the force and inversely proportionate to the mass. The equation would look like this. This is a much more common use of the equation, so I highly recommend that you put this in your equations and use this. Force equals mass times acceleration. And in fact, I will have this equation. This is the one I'll put over on the wall. Net force equals mass times acceleration. F net equals m times A. You'll notice shirts that say, if you've ever seen this, may the MA be with you. And that's, of course, MA equals force. And so it's a play on the word, may the force be with you. May the MA be with you. I've seen those shirts. Back to continuing with that example and circling back around here too. If you remember, I mentioned this in the earlier video. We talked about the force of gravity, which is weight. Weight is a special example of this equation because if we look at this, the force of gravity, weight is defined as the force of gravity, and is equal to mass times acceleration from gravity. Or weight equals mass times 9.8. Because if you live on Earth, acceleration from gravity is commonly expressed as 9.8. That's the standard value we use. So this is what I'm going to put on the wall. This is what you should put in your equations. We commonly show weight as F sub g, which is even more abbreviated form of just F sub grav there. So that is weight, and it's equal to mass times g. And remember, g is acceleration from gravity, and on Earth that's 9.8. So that's where I get the equation weight equals m times 9.8. And this is, of course, actually Newton's second law, because Newton's second law says forces equal mass times acceleration. So that's why you have force of gravity is mass times acceleration due to gravity. That's why this is a special case. Now, this is especially confusing, and I'm going to try to address this right now when we talk about mass. So weight is mass. This is 1,000 grams. This is 1 kilogram. Weight is mass times gravity. Well, how come then when we get a set of a balance here, such as this, or I'm probably familiar with this, you could put this on here and you could say, oh, we're going to weigh it, it's, 1,000 grams, or that's the same as 1 kilogram. Or if you happen to be over in any country other than America pretty much, and you stepped on a set of scales, it would read out in grams. Remember, the SI unit of force is the Newton. We discussed that earlier. The SI unit of force is the Newton, but another common unit, as we said, another common unit is the pound. How come then if you go over to England and ask somebody how much do they weigh, they might say, well, I don't know, 72 kilograms. Well, isn't kilogram a unit of mass? Yeah, it is. But since everyone lives on Earth, what has happened in some cases, instead of folks saying that they weigh 980 newtons, they feel like, I'm guessing it's just a little less embarrassing to say they weigh 100 kilograms. And so it's important to note that while we use the proper unit of force to describe our weight in U.S. customary units, it's very common to use mass to describe what people are meaning to use as weight. What I mean by that is, since we're always on Earth, as mentioned, and G is always 9.8, it's basically like they say, well, let's just forget about that little calculation and let's just say that weight equals mass. In fact, in physics, we categorically can't do that. It doesn't work. There are differences, but if you're trying to describe someone's size, it is effective. And so it's been confusing to physics students forever and ever, getting their mind wrapped around the difference between weight and mass, especially since a lot of the world and in a lot of scenarios we use mass, a unit of mass, which is the gram or the kilogram, interchangeably with weight. I'm hoping that helps. Now if we come back here to this second law again, net forces or unbalanced forces always cause acceleration in the direction of the force. We could go to a situation and we could analyze something like this. You could just look at the pictures. We could look at the size of the arrows. And we could say, well, this arrow upward, the force normal, that's the same size as the force downward. So these forces effectively would cancel each other out. And then we could say, well, we could look at these two forces, the force of air going that's this way and the force applied that way. those are effectively the same size, so they would cancel each other out. They're the same size, opposite direction. So in this case, we would say there's no net force, so therefore acceleration would equal 0. Because remember, net force is 0. We know the mass isn't 0, so therefore acceleration would have to be 0 to get that to be 0, because the net force is 0. This would certainly not be the case over here. These two forces would cancel out because they're equal sized but opposite in direction, the normal force and the gravitational force. But here, the applied force is to the left at a larger quantity than the air resistance to the right. So this would be an example of somebody maybe pedaling really hard on their bike, air is pushing them back, but their pedals on the ground are pushing them forward more. So here, whereas this would cancel out this part, this is in fact bigger. So there would be a net force this direction in this case. And so what would Newton's second law tell us? There would always cause acceleration in the direction of the net force. So here, there would be for sure acceleration. That looks a lot like a 9. There would be in fact be acceleration, and it would be in that direction to the left. So that's just another example of what the second law tells us. Moving on to the third law. It's probably the one everybody remembers the easiest. It's also sometimes, I think, the most difficult to wrap your mind around in some ways. But every action, there's an equal and opposite reaction force. For every action force, there's an equal and opposite reaction force. Sometimes we just say action, there's an equal and opposite reaction. I put the word force in there because I thought it might help. And so an example of this might be, if we take this thing measures pulls, and say I can put a pull here with my hand of, say, 4 newtons. I'm pulling with the force of 4 newtons. Okay? Now, there's a force going this way of 4 newtons, but it's important to note there's also a force going that way of 4 newtons. My hand is getting pulled back that way with a force of 4 newtons. And in fact, we could even prove that. We'll see how close these scales are to being calibrated. We have 2 scales here. If I pull to a force of 4 with one, you'll see the other one does the same thing. They're both pulling the same amount. What would the tension be here on this? Would it be 4 plus 4? No, actually, it wouldn't be 8. Actually, the force of tension here would be 4 newtons. An example of that, if we think about here, so sometimes it can start making your brain do flip-flops. But if you're pulling against a brick wall, a force of 500 newtons, that's no different than somebody standing there and pulling with a force of 500 newtons, such as the elephant. Another way of thinking about this that's sometimes tricky is if you were holding those there, you would be putting a force of 500 pounds on the elephant over here. The elephant, or 500 newtons, the elephant would be putting a force, so there would be 500 pounds going this way. This is really hard to see. 500 pounds that way, the elephant would be 500 pounds back that way, or newtons. Same thing over here, you would have 500 this way, and 500 this way. Now, the thing we have to think about is, remember, net forces always cause, oops, that's the wrong one. Net forces always cause acceleration. Well, is this guy going to be accelerating? Well, we would have to see. So in this situation, you always have to realize there's systems. So this would actually be a system right here. Here you could see these two forces are canceling each other out. That's why the guy wouldn't be moving. Well, what about the elephant? Why isn't the elephant moving to the right? Well, you don't see it, but there actually would be a force on the ground pushing this way of friction. So you can see the elephant's forces would be canceling each other out. Likewise, the car would be putting a force, those wheels would be putting a force on the ground, so it would be canceling out. If all of these forces are the same size, then it wouldn't be moving. The third law, we'll have some more demonstrations and discussions about that coming up, but that is the end of the notes. Thank you and best wishes.